Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about the first law of thermodynamics. So I've previously made a video in which I defined work in a thermodynamic sense. I've also discussed, obviously in other previous videos, work in general, as well as some of the basic concepts that we would want for thermodynamics, such as heat and temperature and whatnot. So let us recall a few things. The first is that in thermodynamics, work, which is always defined as F dot delta X, generally becomes pressure times change in volume for constant pressure. Of course, this equation is for constant force displacement. And then more broadly, if you want work, you take the area under the force versus displacement curve. If you want work here, you take the area under the pressure versus change in volume, or pressure versus volume curve. Okay, second thing to recall is the interplay between heat and temperature and whatnot. Namely, that heat is mass times specific heat times change in temperature, if there's an applicable temperature change, plus mass times latent heat for fusion or vaporization if those processes are applicable. So in some sense, everything in this equation is kind of as applicable. If we have an object and we heat it, we usually think of the temperature as rising, but you could just heat ice and melt it into water and start and end at 0 degrees C, for example. All right, so with those things in mind, we now go to the first law of thermodynamics. The first law of thermodynamics basically says that the change in energy for a system is equal to the heat added to the system less the work done by the system. All right, so the change in system energy is delta U. H in this case represents the heat added or removed from the system. If we add heat to the system, then H is positive. If we remove it, then H is negative. So it's the heat added to the system less the work done by the system or done on the system. So by convention, I use a positive value for W if the system is doing work on its environment. I use a negative if the environment is doing work on the system. In other words, if I have a gas and it's expanding and pushing a piston, then that's work being done by the system, and so W would be positive. If I have a gas that is being compressed by a piston, for example, when you're pumping on a bicycle pump, like a hand pump for your bicycle tire, you're compressing the gas by pushing down the piston. That's work done on the system, and W would be negative. Now note, just so that we avoid any confusion here, we are subtracting W from H. So if I have a system in which I add, let's say, 6 joules worth of heat to the system, and then the system does 3 joules, let's say 4 joules worth of work, then the total change in system's internal energy is now just simply 6 heat minus 4. We did work, so we're subtracting a positive number. 6 joules minus 4 joules is 2 joules. Another thing to note is that if we come back here, I said here heat Q or H is given by this. This is actually no longer quite applicable. It's actually now more true to come in here and say that heat is what you've added to the system, and that if the system does no work, this is how much the heat is. But if the system is doing work, then we have to add a plus W over here. And so this entire side right here that we've previously been calling heat, this is now actually the change in internal energy. put differently, if you have a system that's not doing any work, then the W term over here is 0, and H and delta U should be equal to each other. So in a lot of calorimetry experiments, you're doing things like you have a hot metal block, and you put it in water, and the water pulls heat away from the metal block. So you've removed some heat from the block, and that heat that's been removed from the block goes basically entirely to increasing the water's internal energy, or at least we think that's what it's going to do. But if some of the water vaporizes, becomes steam, and then expands, then also some work is being done, and so some of the heat ends up going into work energy. But on the block itself, you have some heat that's been removed, and the block doesn't really appreciably expand or contract under these circumstances. And so it's not really doing any work on anything, and therefore the heat and the change in the block's internal energy would be equal. And both of these things would actually be negative because the temperature is dropping, heat is being pulled out of the block. Now you could get really pedantic here and say, yeah, but even for a metal block, if you heat something up, the block expands, and if you cool it down, it contracts, and so maybe this block, in fact, could be doing a little bit of work on the environment. For example, if you affix the sides of the block to something else that it can pull or push. But that's neither here nor there. For the most part, we would say that that one is not doing any work, and so heat and change in internal energy are identical. The main point here being that in the previous chapter when we introduced heat, or in the previous set of videos when we introduced heat, we introduced it as heat is these terms. And originally we actually said heat is just mc delta T, should be equal. Then we said, well, phase changes are possible, so maybe it's equal to all this. Maybe there's multiple terms for this because, maybe in steam phase and in liquid phase and in solid phase, maybe there's different specific heats. So there could be 3 terms for this. Fine. But we did not account previously for the fact that this could be doing work. And that's actually a possible source of error for anybody who is doing like an actual calorimetry experiment in a lab. I don't, for my online classes, necessarily do the calorimetry experiment because you end up needing some stuff that I don't feel like making people go out and buy in order to do it. But a lot of Physics 1 courses that you take in a brick and mortar campus may have a calorimetry experiment, and this is just a possible error source. Okay, the other major takeaway to all of this is to pay attention to the signs here. So positive sign for heat means we added heat, negative sign means we removed it, positive sign means work is done by the system, negative sign means work is being done on the system. And we are subtracting W, so if W itself is positive, we're subtracting a positive number. If W is negative, we're subtracting a negative number, which is like adding a plus number. So I'll write those little rule of thumbs down in the next slide. Okay, so our choices basically are we can add or remove heat for the system. We can have the system expanding and doing work on its environment, so work done by the system, or we can have the environment doing work on the system, for example, compressing it. So essentially what you end up getting is, for the change in internal energy, would look like this. Work done by the system, heat added to the system, you'd have H minus W. And I'm going to put absolute values on both of them just so that we know exactly what kind of sign is going in here. This one right here, heat is removed from the system. So we'd have like a negative heat. And work is done by the system. So negative heat minus W. If we have work done on the system, but heat added to the system, then that's like H plus W. This one right here, heat is removed from the system. So delta U, heat removed from the system, means that term has to be overall negative. And then work is being done on the system. That means that term is overall positive. Okay, so this should be very unambiguous as to what sign conventions are being used. What else can we say about this first law of thermodynamics? Well, it basically is the thermodynamic energy conservation. So we could call this conservation of energy for thermodynamics. Let's go ahead and maybe do a couple examples. Let's do some examples. So let's say that you have a system and you've added 800 joules of heat to it, and then while you've done that, the system expands and does 250 joules worth of work. So we want to know by how much is its internal energy raised. So this right here is our heat, and we've been told it's added. So we have plus H. And then it expands and does, so this is W greater than 0, 250 joules worth of work, so this is W. And we want to know how much is the internal energy, that's delta U, how much is that being raised by? So to answer this question, we just use delta U is equal to H minus W. So that's 800 joules minus 250 joules. And that gives us 550 joules worth of change for internal energy. All right, so now let's suppose that this system, whose example we just did, consists of a gas with a known specific heat. So we got this specific heat capacity, C sub P, and then it has a mass of 220 grams. So this would be the mass. All right, and initially we're at room temperature. We want to know what the final temperature is going to be. Well, we should be able to write U, or delta U, is equal to mc delta T, and that means that delta T is delta U over mc. And in the previous problem we had a delta U of 550 joules. Now we have a mass of 220 grams, which in kilograms is 0.22, and we have a specific heat capacity of 0.25 in joules per degree C dot kilogram. So this might require plugging everything into a calculator. We end up getting a delta T of 10,000 degrees C, and so T final is T initial plus delta T becomes 10,025 degrees C. Two comments about this before moving on. One is that this is not really especially realistic, because at such a temperature you might start getting plasma, so you start kind of ionizing the gas, and as a result you may end up not simply having a final temperature as shown. So in some sense ionization is acts also like a latent heat. The second comment is that there's a kind of built-in assumption that C sub P is kind of happening at a constant pressure, and maybe also at a constant volume. So these calorimetry things assume that those are not changing, but they are changing, so your mileage will vary a little bit here. So that was kind of two examples for the price of one, and that's all that I was going to do in today's video. So hopefully you learned something. Thanks for watching.